we can manipulate our confidence interval and why we would even need to manipulate it. So first off, margin of error, affecting the margin of error. We feel like that confidence interval that we just looked at was way too generous. That had a 15% overall spread. So we want to see if we can kind of redesign this study, maybe to be able to get that confidence interval and margin of error a little bit tighter. So we want to get margin of error down to, say, 4%, plus or minus 4%. So instead of having a 15% overall spread from 12.5% to 27.5%, maybe we can get it down to like an 8% overall spread. So margin of error has two components: critical value and standard deviation of the statistic. We have a say in how both of those are calculated. First is critical value. Critical value, we know, is based solely off of what the confidence level. So if I change my confidence level to something that gives me, say, a smaller critical value, then I'll get a smaller margin of error. The other piece we have control over is our other component within standard deviation of statistic, and that's going to be the sample size. So if we were to look at our sample size, so confidence level goes into critical Z, sample size is part of our standard deviation of our statistic. Now we have no influence on what P is, the probability of success in the population, or proportion of the characteristic in the population, but we do have a lot of say so over what our sample size is. So those are the two things that we can manipulate. Certain situations would deem that the one or the other is better. So let's see what's kind of the better in this case. Let's start with manipulating our confidence level so we can get a smaller critical Z. So let's just go ahead and just do the arithmetic and see what that comes out to be. So margin of error, we want it to be 0.04. We don't know what critical Z needs to be yet. Standard deviation of the statistic. Well, we know that we're still dealing with a sample size of 75, but what about this P right here? Now, in this situation here, we do have a prior study we could reference. We know the 10%. We didn't feel good about that because he just made up. Well, we did a sample. We came up with 20%. Maybe that one's pretty good. But let's say that we've never done a study before. If we're starting this process from the very beginning, we've never done this study. No one else has ever done this study. What do we put for P right here? Because we have no baseline for it. So in this situation, you're going to use 0.5 for P. Why would we use 0.5 for P? All right, so the reason we're going to use 0.5 as our best estimate of P is because it provides worst case scenario. What do we mean by worst case scenario? Why do we want worst case scenario? Well, we're trying to get a margin of error as small as possible. Well, worst case scenario is we have a whole lot of variability. So I don't want to assume everything's nice and clean and pretty and we have very little, very tight variability, a lot of consistency from one sample to the next, because now we're manipulating how wide our confidence interval kind of two ways by assuming everything's perfect and nice in the population, and then picking a confidence level that kind of makes that happen as well. So we're going to assume that everything's not perfect and nice, that things are as bad as they can possibly be, and then we'll still get a really good margin of error from that. And if things happen to be better than that, then that just helps us out even more. So we're going to go with worst case scenario, and worst case scenario is getting a 50-50 split. That's the worst thing you can have from a standard deviation of a statistic problem. Why is that? Well, if we just look at the arithmetic right here, if probability of this characteristic or proportion of this characteristic is 0.5, then 1 minus that is also 0.5. So we've got 0.5 and 0.5. We're just going through doing the calculation. 0.5 times 0.5 is 0.25. That's the highest you can ever get when you're multiplying probability of success times probability of failure. Let's just look at what's 0.6 times 0.4. It's 0.24. 0.7 times 0.3, so 70% and 30% split. That's going to be 0.21. 80%, 20% split, that's 0.16. So as you move further and further away from a 50-50 split, you're getting smaller and smaller values on that success failure product. So 50-50 is going to give us the largest possible amount of variability that we can go with. So it's going to provide you that worst case scenario. So that's it every single time. If you don't know P, okay? If no prior studies to estimate P, use P equals 0.5. That's what we're always going to do when we're trying to figure out a confidence level or when we're trying to get a sample size. We would use standard error if we've done the study and we're trying to calculate, because we have a piece of evidence right now. But if we had nothing at all, if this has never been looked at, we have nothing to work off of, we're going to use 50-50 split or as our worst case scenario. So in this course, when I'm asking you to estimate or affect a margin of error based on confidence level or based on sample size, I want you using that 50-50 split. All right, so let's go in and kind of finish through trying to get these calculations. Well, if I divide this stuff out, this is just a number. We divide that over, so you get like a 0.693 equals critical Z. That's all well and good. So we need a 0.693 critical Z, critical value. Well, that's not the question. The question is what's our confidence level? So we need to turn this into a confidence level. Well, how do we turn Z into a confidence level? We look at the standard normal curve that we're associating with it. So my Z's are negative 0.693 up to positive 0.693. And in this, the confidence level is this portion in between those. So we just looked at it a minute ago. So it's the portion in between those two boundaries. So if I want to know how much of a confidence level or how many of the proportions are covered by these two critical values, this is just a normal CDF function. So we're going to do normal CDF. And we know normal CDF asks for 4 features: lower, upper, mu, and sigma. Standard normal curve, mu and sigma are always 0 and 1. The lower, upper in this case are the critical Z's, so negative 0.693 up to positive 0.693. And we're just finding the area in between, finding how many of the sample in the sampling distribution are bound between those two Z-scores. So when we do that calculation, just throw it in the calculator. This one comes out to be 0.512. That's it. That's the answer. That's our confidence level that we would be working with, 0.512. Be kind of weird to say confidence level or I'm 0.512 confident. So I would turn it into percentage. I'm going to turn it into 51% confident. So 51% confidence is the confidence level that you would use to get you to a margin of error if we left everything else the same. Now I want to mention real quick, why did I do 51% instead of say 52%? And you're thinking, okay, well 51.2 would round down to 51. It does round down to 51. But if this was 51.7, I still would have rounded down to 51. Why would I do something like that? Well, it's because of what we're trying to do. We're trying to stay within a margin of error of plus or minus 4. We cannot exceed 4. This is realistically an inequality statement. 0.04 has to be greater than or equal to whatever we come up with right there. So if I had a confidence level that was bigger than 51.2, then a bigger confidence level would cover a bigger area. Bigger area would give me bigger Z-scores, greater distance, so bigger absolute value of Z-scores, and a bigger Z gives us a bigger product. We would have exceeded the 0.04. So whenever you're trying to figure out how to round with confidence levels, every single time, always round down. Always round down. I don't care what that third value is. When we're rounding off a confidence level in the margin of error problem, round down 100% of the time. All right, so that's a confidence level. Now, what do you guys think? Do we think that coming up with a confidence interval that we're only 51% confident in, are going to give us a good argument that our principle's wrong? I don't know. I feel pretty bad saying, well, I'm 51% confident that you're wrong. I feel a lot better if I can say I'm 90% confident that you're incorrect. So, nice to be able to manipulate right there, but I'd rather find a better way where we can still keep a lot of confidence but still tighten that margin of error down. And hopefully that's what our sample size will do. So looking at sample size. So margin of error, just go through our calculations. We know that's got to be 0.04. Again, surely it's greater than or equal to, but I'm just going to do my calculations off of the equals. We need critical z. So critical z, well, inverse norm, and we need area 1 minus 0.90 over 2. Mu is 0, standard deviation is 1, didn't change anything there. And then we need our sample size over here, or our standard deviation of statistic. Still going to use the 0.5 and 1 minus 0.5 for the exact same reason we did right here. We haven't done a study yet, so we don't know. And n is now a variable. So at this point, we have a radical rational equation from your prior math courses. So I don't need to really even show you anything with this one. It's just go through, do your arithmetic, and you're going to get an n out of this. So if we do that, 0.04, we know this is 1.64 because it's the exact same z-score we used a minute ago. 90% confidence level, critical z's are always going to be 1.64. Square root of 0.25 over n. Divide, square both sides, cross multiply and divide, right? I don't have to go through all the calculations on that. So just go through, isolate n, and you're going to get n is equal to 420.25. So that's what your n, what your sample size comes out to be. So at this point, how many students do I need to go and survey? I need to survey 420.25 students. No, I'm not going to survey 420.25 because I can't survey a quarter of a student. I've got to round this off. So I'm going to round this off to 421. And now you're like, whoa, Coach Ferris, why are we rounding to 421? You just said a minute ago, always round down when we're doing these problems. When you're dealing with a confidence level, always round down. And confidence level, always round down. Sample size, you can't round down. Because if I go smaller right here, so if I rounded this to 420.0, okay? I'm getting a smaller sample size, which means I have a smaller denominator. And we know that denominators and numerators have an inverse relation. So if I have a smaller denominator, my overall fraction just became bigger. It's like dividing by 2 instead of dividing by 3, right? Dividing by 2 makes halves, dividing by 3 makes thirds. So when I divide by a smaller number, I get a larger overall quotient. So a smaller sample size gives me bigger standard deviation. We've talked about that before. Small samples have greater variability. Large samples have smaller variability. So if I have a smaller sample size, then I have a bigger variability, which gives me a bigger product, which gives me a bigger margin of error. So because I've got to stay under that 0.04, I cannot, then I have to have at least 420.25. And my sample size has to be at least 420.25, so I can't round down, I've got to round up. So if I'm dealing with confidence levels, I'm always going to round down. If I'm dealing with sample size, I'm always going to round up. Always going to round up in those cases. Now, if I'm looking at these two studies, this one lets me get to stay 90% confident. So I like that. So I get to be 90% confident. I brought in more people, so I've decreased the variability. So I'm feeling really good about this study. But there's one kind of holdup with this study. So changing sample size is almost always the way to go, right? This is the one we like because it has so many benefits and it makes you feel better about your results, gives you more confidence, obviously, in your results and your conclusions, and you're going to decrease your variability as you go. But remember, we have a limit on sample size. Problem I have right here is this 421. Talked at the very beginning, there are about 2,100 kids in the school. This one violates 10% condition. So while it's really, really nice from a confidence standpoint, it violates that 10% condition. And we know that when we violate 10% condition, we violate independence. This formula right here is going to have to be manipulated if we're doing that anyways. So it's kind of finding this balancing act between what's the most confidence I can have and what's the largest sample I can have while still staying within a certain margin of error. So it might not be all one or all the other. The best possible scenario may be I go as many as I can without violating, so I use 210, and then we see what confidence level gets us to that. So it kind of gets into that balancing act of trying to meet all those conditions while still giving ourselves as much information, as little variability as possible. All right, so that's it for estimating a population proportion using confidence intervals, and I will see you guys in class tomorrow.